Chapter 10 of How It Flies, or Conquest of the Air. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Tom Penn. How It Flies, or Conquest of the Air, by Richard Ferris. Chapter 10. Flying Machines. Motors. The possibility of the existence of the flying machine as we have it today has been ascribed to the invention of the gasoline motor. While this is not to be denied, it is also true that the gasoline motors designed and built for automobiles and motorboats have had to be well nigh revolutionized to make them suitable for use in the various forms of aircraft. And it is to be remembered, doubtless to their greater credit, that Henson, Hargrave, Langley, and Maxim had all succeeded in adapting steam to the problem of the flight of models, the two latter using gasoline to produce the steam. Perhaps the one predominant qualification demanded of the airplane motor is reliability. A motor car or motor boat can be stopped, and engine troubles attended to, with comparatively little inconvenience. The airplane simply cannot stop without peril. It is possible for a skilled pilot to reach the earth when his engine stops, if he is fortunately high enough to have space for the downward glide which will gain for him the necessary headway for steering. At a lesser height he is sure to crash to the earth. An understanding of the principles on which the gasoline motor works is essential to a fair estimate of the comparative advantages of the different types used to propel airplanes. In the first place, the radical difference between the gasoline motor and other engines is the method of using the fuel. It is not burned in ordinary fashion, but the gasoline is first vaporized and mixed with a certain proportion of air in a contrivance called a carburetor. This gaseous mixture is pumped into the cylinder of the motor by the action of the motor itself, compressed into about 1/10 of its normal volume, and then exploded by a strong electrical spark at just the right moment to have its force act most advantageously to drive the machine onward. It is apparent that there are several chances for failure in this series. The carburetor may not do its part accurately. The mixture of air and vapor may not be in such proportions that it will explode. In that case, the power from the stroke will be missing and the engine will falter and slow down. Or a leakage in the cylinder may prevent the proper compression of the mixture. The force from the explosion will be greatly reduced, with a corresponding loss of power and speed. Or the electric spark may not be fat enough, that is, of sufficient volume and heat to fire the mixture, or it may not spark at just the right moment. If too soon, it will exert its force against the onward motion. If too late, it will not deliver the full power of the explosion at the time when its force is most useful. The necessity for absolute perfection in these operations is obvious. Other peculiarities of the gasoline motor affect considerably its use for airplanes. The continual and oft-repeated explosions of the gaseous mixture inside the cylinder generate great heat, and this not only interferes with its regularity of movement, but within a very brief time checks it altogether. To keep the cylinder cool enough to be serviceable, two methods are in use: the air cooling system and the water cooling system. In the first, flanges of very thin metal are cast on the outside of the cylinder wall. These flanges take up the intense heat, and being spread out over a large surface in this way, the rushing of air through them as the machine flies, or sometimes blown through them with a rotary fan, cools them to some degree. With the water cooling system, the cylinder has an external jacket, the space between being filled with water, which is made to circulate constantly by a small pump. In its course, the water, which has just taken up the heat from the cylinder, travels through a radiator in which it is spread out very thin, and this radiator is so placed in the machine that it receives the full draft from the air rushing through the machine as it flies. The amount of water required for cooling a motor is about 1 1/5 pounds per horsepower. With an 8-cylinder 50 horsepower motor, this water would add the very considerable item of 60 pounds to the weight the machine has to carry. As noted in a previous chapter, the McCurdy biplane has its radiator formed into a sustaining plane, and supports its own weight when traveling in the air. It is an unsettled point with manufacturers whether the greater efficiency, generally acknowledged, of the water-cooled engine more than compensates for the extra weight of the water. Another feature peculiar to the gasoline motor is the necessity for such continual oiling that it is styled lubrication, and various devices have been invented to do the work automatically, without attention from the pilot further than the watching of his oil gauge to see that a full flow of oil is being pumped through the oiling system. The electric current which produces the spark inside the cylinder is supplied by a magneto, a machine formed of permanent magnets of horseshoe form, between the poles of which a magnetized armature is made to revolve rapidly by the machinery which turns the propeller. This magneto is often connected with a small storage battery or accumulator, which stores up a certain amount of current for use when starting, or in case the magneto gives out. The great rivalry of the builders of motors has been in cutting down the weight per horsepower to the lowest possible figure. It goes without saying that useless weight is a disadvantage in an airplane, but it has not been proven that the very lightest engines have made a better showing than those of sturdier build. One of the items in the weight of an engine has been the flywheel, found necessary on all motors of 4 cylinders or less to give steadiness to the running. With a larger number of cylinders, and a consequently larger number of impulses in the circuit of the propeller, the vibration is so reduced that the flywheel has been dispensed with. There are several distinct types of aircraft engines, based on the arrangement of the cylinders. The tandem type has the cylinders standing upright in a row, one behind another. There may be as many as 8 in a row. The Curtiss and Wright engines are examples. Another type is the opposed arrangement, the cylinders being placed in a horizontal position and in 2 sets, one working opposite the other. An example of this type is seen in the derrick motor used in the Santos Dumont monoplane. Another type is the V arrangement. The cylinders are alternately leaning to right and to left, as seen in the Fiat engine. Still another type is the radiant, in which the cylinders are all above the horizontal and disposed like rays from the rising sun. The 3-cylinder Anzani engine and the 5 and 7-cylinder REP engines are examples. The star type is exemplified in the 5 and 7-cylinder engines in which the cylinders radiate at equal angles all around the circle. The double opposed or cross-shaped type is shown in the Gobron engine. In all these types, the cylinders are stationary and turn the propeller shaft either by cranks or by gearing. An entirely distinct type of engine, and one which has been devised solely for the airplane, is the rotative, often miscalled the rotary, which is totally different. The rotative type may be illustrated by the Gnome motor. In this engine, the 7 cylinders turn around the shaft, which is stationary. The propeller is fastened to the cylinders and revolves with them. This ingenious effect is produced by an offset of the crankshaft of half the stroke of the pistons, whose rods are all connected with the crankshaft. The entire system revolves around the main shaft as a center, the crankshaft being also stationary. Strictly speaking, the propeller is not a part of the motor of the flying machine, but it is so intimately connected with it in the utilization of the power created by the motor that it will be treated of briefly in this chapter. The form of the air propeller has passed through a long and varied development, starting with that of the marine propeller, which was found to be very inefficient in so loose a medium as air. On account of this lack of density in the air, it was found necessary to act on large masses of it at practically the same time to gain the thrust needed to propel the airplane swiftly, and this led to increasing the diameter of the propeller to secure action on a proportionally larger area of air. The principle involved is simply the geometric rule that the area of circles are to each other as the squares of their radii. Thus, the surface of air acted on by 2 propellers, one of 6 feet diameter and the other of 8 feet diameter, would be in the proportion of 9 to 16, and as the central part of a propeller has practically no thrust effect, the efficiency of the 8-foot propeller is nearly twice that of the 6-foot propeller, other factors being equal. But these other factors may be made to vary widely. For instance, the number of revolutions may be increased for the smaller propeller, thus engaging more air than the larger one at a lower speed, and, in practice, it is possible to run a small propeller at a speed that would not be safe for a large one. Another factor is the pitch of the propeller, which may be described as the distance the hub of the propeller would advance in one complete revolution if the blades moved in an unyielding medium, as a section of the thread of an ordinary bolt moves in its nut. In the yielding mass of the air, the propeller advances only a part of its pitch, in some cases not more than half. The difference between the theoretical advance and the actual advance is called the slip. In practical work, the number of blades which have been found to be most effective is 2. More blades than 2 seems to so disturb the air that there is no hold for the propeller. In the case of slowly revolving propellers, as in most airship mechanisms, 4-bladed propellers are used with good effect. But where the diameter of the propeller is about 8 feet and the number of revolutions about 1200 per minute, the 2-bladed type is used almost exclusively. The many differing forms of the blades of the propeller is evidence that the manufacturers have not decided upon any definite shape as being the best. Some have straight edges nearly or quite parallel, others have the entering edge straight and the rear edge curved, in others the entering edge is curved and the rear edge straight, or both edges may be curved. The majority of the wooden propellers are of the third mentioned type, and the curve is fashioned so that at each section of its length the blade presents the same area of surface in the same time. Hence the outer tip, traveling the fastest, is narrower than the middle of the blade, and it is also much thinner to lessen the centrifugal force acted upon it at great speeds. Near the hub, however, where the travel is slowest, the constructional problem demands that the blade contract in width and be made stout. In fact, it becomes almost round in section. Many propellers are made of metal, with tubular shanks and blades of sheet metal, the latter either solid sheets or formed with a double surface and hollow inside. Still others have a frame of metal with blades of fabric put on loosely so that it may adapt itself to the pressure of the air in revolving. That great strength is requisite becomes plain when it is considered that the speed of the tip of the propeller blade often reaches 7 miles a minute, and at this velocity the centrifugal force excited, tending to tear the blades to splinters, is prodigious. Just as the curved surface of the planes of an airplane is more effective than a flat surface in compressing the air beneath them, and thus securing a firmer medium in which to glide, so the propeller blades are curved laterally, across their width, to compress the air behind them and thus secure a better hold. The advancing side of a blade is formed with a still greater curve to gain the advantage due to the unexplained lift of the paradox airplane. Where the propeller is built of wood, it is made of several layers, usually of different kinds of wood, with the grain running in slightly different directions, and all carefully glued together into a solid block. Ash, spruce, and mahogany in alternating layers are a favorite combination. In some instances, the wooden propeller is sheathed in sheet aluminum. In others, it is well coated with glue, which is sandpapered down very smooth, then varnished, and then polished to the highest luster, to reduce the effect of the viscosity of the air to the minimum. In order to get the best results, the propeller and the motor must be suited to each other. Some motors which race with a propeller which is slightly too small work admirably with one a little heavier or with a longer diameter. The question as to whether one propeller or 2 is the better practice has not been decided. The majority of airplanes have but one. The Wright and Cody machines have 2. The certainty of serious consequences to a machine having 2, should one of them be disabled, or even broken so as to reduce the area, seems to favor the use of but one. End of section 10.